I'm Rich DeJong. I'm now Professor Emeritus at Calvin College, where I've been for 26 years. Take retirement from teaching and committee work to do more research. So I'm enjoying my second career at Calvin, doing more research than I have been able to do in the past. As a graduate student, D.Lyon was my advisor, my thesis advisor. And while I took a course with him on SEA, like most graduate students of his, we avoided SEA at all costs on our theses because SEA was way too complicated for us to think about possibly making a contribution to. So actually I did my dissertation with Dick on diesel engine noise and vibration. And then I went to work for the company that he started, Cambridge Collaborative, along with Jerry Manning, and worked my way up to vice president there. But very early on in my career, Dick continued to get me engaged in SCA-like projects. And so gradually I eased my way into understanding some of the equations that he had developed that were very complicated, and started developing software, the same computer program, to implement it. And then I decided myself, I always knew I wanted to get into teaching, so I decided to look for a place to teach. And Calvin was a good mix because they let me both teach and do research. And it was after I moved there that Dick started talking to me about working with him on a second edition to his book. And he wanted the second edition to be at least half applications. His first book was all the theory, very limited applications. But now that there had been so many projects that we had worked together on, that he wanted me to write the second half of the book on exactly how you implement SCA in a practical sense. Yeah, so we worked on that for a number of years. Eventually got it published in '95. So that's when I tell people that's when I really was able to understand most of what Dick did in SCA. But I still tell people there's some things in the first chapters of the book that I don't thoroughly understand because they're extremely complicated mathematical derivations to come up with the basics of SEA. Well, yes, but initially I thought we'd just revise it and correct some of the typos and keep the basic format. What I learned is that many people get hung up on themselves not being able to get through the first 4 chapters. And so the next edition will be quite a major revision. And it will leave a lot of the complicated mathematical derivations to the end, or the appendices, and focus more on the basic concepts of modal density, which is so important to SCA, and the coupling loss factor, which is the one unique feature of SCA. Modal density was known and used before SCA. And the damping loss factor was known and used for many other areas. So Dick's formulation was unique in that as he tried to do the transmission function, the transfer function, representing it in the same format as a damping loss factor, so he called it a coupling loss factor. And there's lots of misunderstanding about that. There's great confusion over how to come up with that. And there's actually some very simple, basic procedures to follow to understand coupling loss factors. And so that's those main issues, modal density and coupling loss factor, I will start with in the next edition so people understand how that relates to the dynamics of complex systems. Well, it comes from, I'm involved in noise and vibration from a much broader sense than SCA. However, whether you're using finite element analysis, statistical energy analysis, most of those numerical tools are basically looking at the transfer function. If there is an excitation, how much does the system respond? And early on in my career, I realized that that's a small part of the problem. in many cases, well, the typical model that we present is source, path, receiver. So the transmission function, transfer function is the path. And the psychoacoustic people talk about the receiver and what impact and sound quality, what impact does the people have in terms of whether they like the sound. So that's another area, but the huge area is the source. Mm-hmm. And unless you characterize the source, you're not going to have a usable engineering tool. And most of, when I started working in particular computer analysis, as well as analytical analysis, most of that was based on point sources. A point force or a monopole or dipole, localized source. What does the system respond to that? Well, if you look at a transportation vehicle, an aircraft or a boat or a car, there are no point sources. They are distributed sources. So that's one of the reasons why early in my dissertation I worked on diesel engines. It was the same thing. People used a pressure in the cylinder as a point monopole source. Well, no, there's distribution of pressure in the cylinder. And the gears are distribution of forces. So I was very much intrigued by the fact that along with doing transfer function analysis, one had to develop the source excitation. So early days it was engine, and acoustic intensity was developed to get the distribution of radiation from the engine, not just calling it a equivalent point source, which was the models that were used when I started. But no, directivity, what effect does it have when it's in an engine compartment, how it's rotated. Same thing with the aircraft engine and so forth. So the engine was the first variable. And then tire noise, same thing. The directivity of the tire noise is very important. But as you mentioned, most recently I've been working with wind noise, because wind noise is, again, a very unique source. It's a distributed source, so you have to understand spatial matching, how the distributed field of the pressure excites both the acoustic field and the structural field. So that all fits in with whatever kind of computer simulation you want to do. You have to be able to analyze distributed forces, and wind noise is perhaps the most challenging one. That's a very good question. Because my career spans the days of the beginning of the computer implementation to where it's now heavily relied upon. In my early days, whenever I tried to do a computer simulation, the generation that I inherited acoustics from, DeJong and DeJong, they would say that's a problem, because it's going to get in the hands of people who don't understand. Now, to them, understanding meant knowing the mathematical equations, and so they wanted to have the knowledgeable people well versed in the mathematical formulations. And there was a tendency to, therefore, only work on simple problems, because you can only do closed form mathematical solutions on simple problems. But something like SEA and a few other methods were trying hard to take a different approach, and that is to have approximate solutions to very complicated problems. And so to me, it was very natural then to say, well, fine, then a computer, you ought to be able then to use a computer program to do that kind of solution, that kind of computation, an approximate solution to very realistic problems, realistic geometries. And so, since finite element was having such great success, then it was very natural to say SEA and other methods should also, because we did wave number transmission functions, integrating integrals, so a number of computer simulations to try to do computations that you could not do by hand. And so I think that field is very mature. I think that has lived up to the expectation of those of us who promoted it. But those who didn't promote it, those who were skeptical of it, were also right, and that is that if you have such a tool, there's a tendency to misuse it, to not understand the complexities, to just say, if I just import the geometry and push a button, I can get a good answer. So in some sense, it hasn't changed in the sense that you could say the same thing about mathematical formula. If I just derive some integral equation, I might be totally missing the point. But it's just gotten to be where you can do realistic-looking problems and have no idea what's going on. So I don't know what the future is, but what I hope the future is that the field goes to understanding the need to calibrate the systems. And I've always used the analogy that if you get a new measurement system, it's very natural in the industry of measurement and in the training of measurement to say, you must calibrate your system. You must measure known quantities. You must compare your calculations to a standard before you would ever dream of doing a measurement. And people who don't do that oftentimes then risk failure because they don't appreciate the fact that they need to calibrate their equipment. So that's very much a part of the measurement system. I feel the same thing now that the computational field is quite mature. I'm hoping that there's a growth in the area of understanding that you must first calibrate your system. You must go through the effort, which seems like a waste of time to many, to compute, to calculate known quantities, to make sure that you can accurately compute known results, and then you have confidence to extrapolate to the next step. So, in the finite world, they have standard computations that were there for the program's development. Programs, in order to be qualified for rigorous consideration, had to show that they could compute certain types of simple calculations. But in terms of dealing with complex systems, there are no standards. How do you know if someone does a complicated model, whether it's useful or not? And so I'm hoping that that's what that the industry works on, and that is how do you calibrate a numerical, your use of a numerical computation. I think the noise and vibration community is in good hands with the next generation. And those of us who have been around for a number of years always, I think, worry about that. But when I look back, I think I didn't know a whole lot when I started. And I was very fortunate to have mentors who not only worked at making sure I knew what I was doing, but they entrusted me with taking on the challenge. And I have to say, the next generation is at least as if not more capable than I was when I started. And so while there are many detractors that say, oh, well, the students coming out of school nowadays don't have. No, they're a very capable group of people. And so I'm looking forward to working with the younger crowd as much as I'm hoping they're still interested in working with me.
Rich, thank you very much.
Very good. My pleasure.